Hi, this is Brett McDonald, instructor for Atmospheric Science 2000 Introduction to Meteorology. Today we're going to be going over Chapter 3 on solar and terrestrial radiation. The driving question for this chapter is to investigate how energy flows in and out of the entire Earth atmosphere system and ends up being in a balance in order to make the planet on which we live habitable for us. In addition, we'll also discuss ways where that energy can be changed or modified and thus create an imbalance and see what occurs when that does. So let's look back in time. Obviously, tracking the sun, starting off talking about solar radiation, has been a very important part of life, looking at seasons and years and everything that goes on. Stonehenge is a very good example, something that still exists where people tried to track the yearly cycle. Native Americans also did the same thing. Here's a picture of wooden posts arranged in circles to also track a calendar. Here in Wyoming, there are some examples of medicine wheels, the largest of which is in the northern Bighorns, up east of Lovell. There's also places in Egypt and Peru that also strove to or tried to predict these important events on the yearly calendar for people to pay attention to. Let's get into it. Solar radiation, it's all energy, and energy can be classed by certain properties, both, as it says here, both electric and magnetic properties. When we talk about the energy, we usually talk about the electromagnetic spectrum and how it's divided up based upon the wavelength of the energy waves, going all the way from very large wavelength radio waves to infrared radiation to the visible light that we see with our eyes, even, and then down onto X-rays, which is even smaller. So let's get some basics down. So wavelength, when we're talking about wavelength, we're talking a wavelength is basically the distance between the crests of the wave, or actually any common feature of a wave. Here in this example on the right, you can see from the top of the wave to the top of the next wave. You could also do it from the bottom of one wave to the bottom of another wave. So that's the wavelength. And when that distance is long, it's obviously long wavelength, and then it's called a low frequency because it occurs more slowly. When that wavelength shortens up, it's a high frequency. So again, the key here is recognizing that quantitatively, a large wavelength is inversely proportional to the frequency of that is. So radio waves, as mentioned, are actually very different. They can be as small as centimeter or smaller to hundreds of kilometers. Thus, that's why they can travel and bend with the Earth's atmosphere. Microwave radiation, and that is kind of next down onto the scale that we look at. Again, this is one that microwave energy particularly works on certain kinds of materials. We know water. That's why it's used in microwave ovens. Incidentally, the Doppler radar that is up at the office here in Riverton also works on that same wavelength. It's microwave signals that are sent out because we want it to interact with the water in the atmosphere. Going down, then we have ultraviolet radiation. Then we have the visible radiation. That's, again, the spectrum. We're down to, as it says here, on the order of a millionth of a meter, micrometer, 0.4 micrometer for violet, 0.7 micrometer for red. So it's a very small range, but that's the range that our eyes can perceive. And then even smaller than that then is infrared radiation. And we'll see how those impact it. There are some particular scientific laws that have been discovered that govern radiation. One of those that's discussed is trying to refer to things as black bodies. Basically, a perfect black body will absorb all of the radiation that comes into it and then also emit it perfectly. There really is no such thing as a perfect black body, but some things are close, and so we can approximate it, especially for particular wavelengths. But nothing is a perfect black body. So the key here, and we'll see this on the next slide, is that the wavelength of the radiation that gets emitted by a black body, again, is inversely proportional to the temperature, which understands a lot of what kind of radiation do we typically get from the sun because it's hotter, and what kind of radiation occurs from the earth because it's cooler. So there's one law called Wien's displacement law. Again, that maximum, that wavelength, is inversely proportional to the temperature. So in this instance, with the graph on this side, you can see that as the never mind, it's not showing exactly what I wanted to show in this instance, but it does show a little bit of how that different wavelength relates to different potential. Probably it shows intensity. I thought it was going to show temperature, but we'll see next. Another law is called the Stefan-Boltzmann law. Again, the energy that is emitted by a black body is proportional to the fourth power of the absolute temperature. We won't be using these necessarily to calculate anything particular in the course, but we will be. You want to know these as some of the basics. We'll skip some of these slides here. Another thing to remember is what's called the inverse square law. Basically, that the energy that's received is inversely related to the distance from where it's coming from. In this case, the sun. So in this kind of explaining how Mars gets so much more energy than the Earth and Venus do. So let's get to that basic nature of where the radiation comes from that drives everything on the Earth. Well, it all pretty much comes from the sun. The sun itself is composed of hydrogen and helium, and so there's nuclear fission reactions that are taking place. I admit it's been a very long time since chemistry class, but again, because of the nature of the reactions and the energy that comes, that's where it's coming from. And so when we look at the different parts of the sun through the cool instruments that we have, there's some things that we need to pay attention to. The part that we can see is called the photosphere, and it's obviously cooler than what's on the inside. And there is somewhat of a convection nature, meaning things bubble and move around according to their heating and cooling. And so we can see that as our instruments take pictures. Some of those bigger areas, especially the cooler areas, are the sunspots. And it's interesting, the sun actually goes through cycles where it has more and less sunspots determine what's happening. So you could imagine then that as there are more sunspots, because they're cooler areas, we get less energy, and it can affect then the overall energy that's coming into the Earth. Then there's the chromosphere, which is kind of like the outer portion that we see when it has bursts of gases coming from the surface and the interior. So what's really key? What really drives how solar radiation impacts us? Well, one big thing is what's the angle, depending upon where we're at on the planet. Is the sunlight coming straight in, like in flashlight A, or is it coming at an angle? This is dependent upon not only where you're at on the Earth, but the time of the year. You could think of flashlight A as a lot of how sunlight comes into the equator, whereas up here in Wyoming, it's usually more at an angle. And so the same amount of radiation actually spread out over more of an area. Explains a lot about what we see on the Earth. Great picture here again, showing how the same energy output from the sun is coming in, but yet at the equator, it has less of the distance through the atmosphere until it impacts the Earth, as compared to somewhere up in the mid and northern latitudes where the atmosphere actually impacts, there's a longer time that the sunlight's coming in, and it impacts what reaches the planet. Now this does changes. There's some equations that can be used, but again, remember at the equator, we're typically thinking that it's a 90 degree angle. We're almost at the spot here, Riverton. We're at about 43 degrees, and so we're almost halfway to the pole. And then right at the poles, when you're right at one of the equinoxes, it's just coming straight in and not really impacting the poles very sharply at all. So that angle that we're talking about is called the solar altitude. And so it's important to know how that solar altitude changes on different locations of the Earth as the Earth tilts back and forth through the cycle of the year. Here's a couple of different locations that you can see that change. So again, what we're graphing on the y-axis is the average daily solar radiation, and then along the x-axis is going through each of the years of the month for different locations. Now, Singapore is a place that's very, very close to the equator, and so as we could assume, this amount of solar radiation is almost the same. There's just a slight variation. If we look at a place that's about halfway in between, very similar to us in Wyoming, but Brockport, New York, let's see, that's the green one. There's actually very little in the wintertime, December, January, February, but then as we go into summer, we actually get more, because of the tilting of the Earth, we actually get more solar radiation than Singapore does. And then as we go back into fall and winter, it goes back down again. Now, a place, either North Pole or South Pole, Antarctica in this case, Antarctica actually gets its most in the Northern Hemisphere winter, Southern Hemisphere summer. And because it's right at the pole, it actually goes to zero. It actually doesn't get any for many months through its winter, and then it comes out again. So it's important to remember again, December 21st, June 21st are called solstices, and in March 22nd, 23rd-ish, and September 23rd are called equinoxes. So again, the December and June is when the Earth is tilted its most, either bringing more into the northern hemisphere or more into the southern hemisphere. And then the equinoxes are when the Earth is straight up and down. And so the sun is at a perfect 90-degree angle right on the equator. Already explained that, but yeah, so just again, remember those different things. Here's a pretty rough schematic of where the Earth might lie with the sun. One interesting thing is that actually, and this is true, so the Earth does not rotate around the sun in a perfect circle. It's a little bit oblong at the present time. The time that the Earth is actually farthest away from the sun is in the northern hemisphere summer. And then when we're the closest to the sun is in the northern hemisphere winter. Good thing for us, if it were reversed, I think our winters would be harsher and colder, and our summers would be hotter. So it's kind of a good thing. And this is a nice schematic showing how at those different times of the year, how the Earth is necessarily tilted. So on the left here, when we're in our winter in the northern hemisphere, you can see that the North Pole is tilted away from the sun, and then it goes back at the equinoxes, and then in the summer, or how that tilt is pointing, giving northern hemisphere the more sunlight in the summertime. So let's kind of getting down again at equinoxes, and actually so at the equinoxes, when the tilt is perfectly aligned with the incoming solar radiation, everywhere is getting 12 hours of sunlight. This is what it might look like from the satellite imagery that we're able to take. And now when we're in our summer, you can see that when the satellite looks at it, you can see more from the visible satellite in the northern hemisphere than you can in the sun. You can almost see the tilt as the sun is impacting the northern hemisphere more than it does the southern hemisphere. And then the opposite is true, where we're getting less sunlight during our winter, and the southern hemisphere gets more. So again, another schematic just kind of showing the potential changes in the solar altitude for different places at the equator. You can see that the differences just go back and forth. But again, you're getting a lot of solar radiation at the equators. Now in a place like us in the mid-latitudes, again, the sun is never directly overhead because we're so far north at 43 degrees. And so it's actually on June 21st when it's the highest in the sky, and then it slightly changes. And then again, here's where you look at the poles and you can understand why the North Pole goes through so many months of dark. And then also in the summertime, why they get just continuous sunlight as well. So again, another graph showing the duration of sunlight at particular locations. Here, let's look at our closest, Denver. You can see that at the max, we're probably right around 9 hours during winter solstice. But then in the summertime, at summer solstice, our longest day is about 15 hours. All right. So some other things that go into some of the calculations in determining these, there's a solar constant that is used in equations to describe the amount of energy that's coming based upon the area that it's coming into on the Earth. We'll kind of skip through this. This just shows, again, the different amounts of energy based upon the latitude for all the way from the South Pole to the North Pole. So what happens to the sunlight, the solar radiation, as it comes in? Well, actually a lot of different things because of the atmosphere, because of the various particles and everything. We have light and energy that's scattered, we have it reflected, and we have it absorbed. And so as we look at, again, various radiation laws, we want to make sure that when we're trying to add it all up, that it all equals 100% when we look at things. So when we're talking about scattering, we're talking about energy that comes from the sun, and for whatever reason, it hits some kind of a particle in the atmosphere and it scatters around. That's why the sky looks blue, is because there is particular scattering that occurs because of oxygen and nitrogen molecules that are in the air, and they're preferred with that blue wavelength. I remember actually going almost like a proof algorithm of this in a class in college to show that. Another thing that happens at solar radiation is it's reflected. So this is where that energy comes in, and it's not necessarily scattered, but it's actually just basically returned right back. This happens with things a lot because of their characteristic, almost their color mostly. And so that's why some particular things that are white actually are reflecting a lot of that back, whereas black or darker things absorb. And so that's where we're going to introduce the term albedo. So an albedo is defined by the fraction of the radiation that is scattered back by either a surface or the particles. So something that has a high albedo sends a lot back, whereas a low albedo actually absorbs more and doesn't reflect very much back. We'll look at some different things later with that. The other thing that happens is absorption. Some of that energy can actually get absorbed by particles in the atmosphere or on the surface. One of the really cool things that has been researched for quite a while is how particular molecules, especially ozone, absorb ultraviolet radiation in particular parts of the atmosphere, especially up in the stratosphere, and reduces the amount of ultraviolet radiation that comes to the Earth. And so this kind of shows where the concentration of the ozone is and how far it is above the Earth. Again, it's up in the stratosphere, and how that we need that ozone up in the stratosphere in order to keep the ultraviolet radiation that comes to the surface of the Earth at a minimum. Here's a nice graphic which shows how ozone can both be produced as well as destroyed by the processes that go on up there. So one of the things that was found was that there were particular chemicals that we were putting into the atmosphere that were actually helping to destroy ozone and not replenish the ozone. And so that stratospheric ozone shield was diminishing. And those were identified as chlorofluorocarbons, or CFCs. And so beginning in the late 70s and 80s, those started to be banned. And you probably have heard a lot about the how it's helped. Reducing those into the atmosphere has helped bring back, strengthen the ozone shield. Know, though, however, that because of things that particularly go on around the Earth, there is still somewhat of what's called an ozone hole, especially occurs around Antarctica. And it occurs, again, because of some natural things that happen. Again, elsewhere, it's strengthening, but that there is still an ozone hole that occurs around Antarctica because of, again, the amazing conditions that occur during certain times of the year. It doesn't happen over the northern hemisphere, over the Arctic, because of, again, different conditions, warmer temperatures. It's a combination of the colder temperatures and the really strong circulation over Antarctica that causes this ozone hole over in the southern hemisphere. So again, getting back to albedo, let's look at some different values of albedo for different surfaces. Again, remember that bright white things are typically going to have your highest albedos. For us around here right now, that's going to be fresh snow and clouds, really bright clouds. Things that have a low albedo means they're absorbing more solar radiation are going to be dark things. So again, your pine trees in the forest, your roadways, dark, open ground, open dirt as compared to sand, green crops compared to other types, and even water in and of itself, whether you're looking at it directly, the light directly coming in or coming in at an angle. So if we look at the, let's see, what was the spot where we had the overall albedo of the Earth? I can't remember what that was. But again, just to reinforce, again, the lighter a surface is, the higher the albedo, the more that light is reflected back. So again, here's a little graphic which indicates why water, again, appears blue and almost greenish tint to our eyes. It's because of how water absorbs different types of light. Again, it says here water absorbs the red light more efficiently, and it doesn't on the blue and greens. That's why our oceans and our lakes and everything appear green or blue because of that. Here it is. So if you average everything that's going on, as if you were on over the whole Earth looking down, the average albedo would be about 30%. And so that we can take that and basically put that back into our little algorithm that we talked about earlier. And so say that's a total reflectance of the Earth. So let's say that's 30%. They estimate that there's about 23% that's absorbed by the particles in the atmosphere. And there's another 47% that's actually absorbed and makes its way all the way down to the Earth's surface. So again, we're just going to go through some slides which show that absorption in the atmosphere occurs with different particles in the atmosphere based upon different layers. Here's like that stratospheric ozone. You can see why it's warmer, actually, relatively up there because of that absorption and cools. There's a lowering spot near what's called the difference between the stratosphere and the troposphere, which is called the tropopause. And then here where we live at down at the ground, it's warmest, which is we're grateful for. Makes it livable for us. So looking at things again, everything that our Earth atmosphere system does is wants to create a balance. And so there's this kind of equilibrium that goes on. So as the Earth atmosphere receives solar radiation, it also gives off radiation in order to maintain that balance. So as you may have read or learned about already, there is one of the things that enables the surface of our Earth to this planet to be warm enough for us to live is that there is something called a greenhouse effect going on. There are gases in the atmosphere which help to keep heat in the lower part of the atmosphere and keep it at a level where we might be able to live. So when we talk about the greenhouse effect, that's actually a good thing. We want the greenhouse effect to occur in the atmosphere in order for it to be warm enough for us. Again, another little schematic showing how sunlight comes in. Some of it's reflected, most of it gets absorbed, and then the Earth and the atmosphere give off part, but the atmosphere itself sends energy back to the Earth's surface. This would not occur if we had an atmosphere that did not contain these greenhouse gases, likely something like Mars. If you have an atmosphere that has an overabundance of greenhouse gases, then your surface of your planet is going to be extremely warm, and Venus is a good example of that. So here at the surface of the Earth and the atmosphere, because of the temperature, it emits infrared radiation, as we described at the beginning of the chapter. Let's move on. So that's what helps to keep both the Earth again in the atmosphere in this stable thing and keep us with our temperature and keep us with the warming that we need. So again, they've tried to estimate what types of what impact some of these greenhouse gases are. We usually talk about carbon dioxide and methane and some others being greenhouse gases. But actually, the primary greenhouse gas is water vapor itself. Water vapor contributes half or more of the warming that goes on within the atmosphere and the Earth in order to keep it. However, carbon dioxide and methane and other particles, they actually do more per individual molecule. But when you look at the overall percentage of those gases, there's a lot more water vapor than there is carbon dioxide in the atmosphere. Hopefully we went through that somewhere in chapter 1 or chapter 2 of the textbook. So let's move on here. This is just, again, a schematic of how different gases, methane, nitrous oxide, oxygen and ozone, carbon dioxide, how they actually absorb and emit different wavelengths of infrared radiation. Not only, visible and infrared radiation. And so it's important, actually, kind of necessary and good that we have all of those different particles and how they each do their own. Just so that you know, the whole concept of a warming atmosphere and stuff isn't something that's just been known in the last 20 or 30 years. It's actually something that has been known prior to that. There was a climatologist/meteorologist previously named Guy Callendar. And so there's what's called the Callendar effect. And he's the one who actually predicted that as carbon dioxide increases in the atmosphere because of man or nature, that the temperature would actually go up. And so we'll look at this a lot more later on, But there's a really great observing site on top of Mauna Loa in Hawaii, which has and other parts of the world that monitor carbon dioxide in the atmosphere at a higher location, kind of in a free atmosphere situation. And you can see how since they started this in the late 50s, the concentration of carbon dioxide in the atmosphere has actually gone from about 310 parts per million, and now we're nearing and probably we're over 420 parts per million. These are a little bit older graphs, and we'll be looking at some newer graphs. Studies have been done, have shown that yes, there are some natural things going on that are leading to carbon dioxide increase, but it's pretty obvious that most of the carbon dioxide increase is due to fossil fuels putting out more carbon dioxide, getting it into the atmosphere. And unlike water vapor, carbon dioxide takes a lot longer time to cycle through the atmosphere, so it stays up there much more. And looking back at previous studies, previous records, trying to look at ice cores and other types of things, as far as we can tell, this is the highest that we've ever seen carbon dioxide concentration in the atmosphere. So we're also, again, as I mentioned before, methane is another carbon dioxide gas, and it's on the increase as well. It comes out through a bunch of different things that we do as humans here upon the earth. Nitrous oxide also is another one that is on the increase. It's being tracked. Good thing, tracking of those chlorofluorocarbons for the ozone is actually leveling off or decreasing, which is helping out the situation. So again, going to the whole thing is we're extremely confident that human activities are causing the increase in the in these gases, which is leading to a warming. It's leading to an imbalance of what was there before, and so as a result, the whole Earth atmosphere system is having to warm because of the increase in the energy that is being kept within the Earth atmosphere system. There are some pretty big risks that are occurring. We'll look, as you do chapter 15 on climate and climate change, you'll look more at that as well. So there are obviously a lot of negative effects that we've talked about with the climate change, health, sea level rising, the acidification of the oceans, the melting of glaciers, all kinds of potential. Interestingly, there are some potential positive impacts. With warming, you can see longer growing seasons. With warming, you can see places where ice is not as strong or not as existent, where we might be able to navigate ships and things like that. Potentially, overall, less heating. But on the flip side, you'd need to air condition more because things are getting warmer. This year in Wyoming, especially here in Fremont County, it has been interesting because it's been so cold. Now, that's not to say that global warming is a hoax or false. There are ups and downs. Let me go back here. Just like the yearly change in carbon dioxide occurs because of other things going on, if you were to look at average temperatures, there's ups and downs. But as a whole, when you look at things on a global scale and over years and decades, there is a warming going on. And that's why we need to look, when you think about stuff like that, global climate change, you have to look at a much longer period than individual events, like the 2 times that we've hit negative 30 here in Riverton. You have to look back over a longer period, like we typically do, to when we had somewhat reliable records in the late 1800s all the way to now. But overall, there has been an increase in the average temperature, not only on land, but in the ocean, and then the whole Earth atmosphere system. Kind of said that. So that's why there's so much discussion now about trying to cut fossil fuel consumption and burning, and try to figure out a way that we can reduce the amount of carbon dioxide and other strong greenhouse gases into the atmosphere. So I think that is about it. There's a couple ways that we talking about here that we monitor it, but this is might not be the most interesting chapter that you might think about, but it's very important to understand where our whole Earth atmosphere system gets its energy, how the energy moves around, and what can cause changes to those energy balances that are in this amazing Earth atmosphere system that we have. Thanks a lot for taking time to listen. And again, refer to your textbook for more information and be sure to ask questions. Thanks.